Hello! In this video, we are going to prove the following theorem. Suppose G is a group and A is an element of G. Then the order of A is equal to the order of the group generated by A. Now, by definition, the group generated by A is the set of all elements of the form A to the K, where K is an integer. And let's remind ourselves of the concepts of the order of a group and the order of an element in a group. Now, the order of a group is just the number of elements in a group. Given a group G, if G is finite, then the order of G is equal to some positive integer n. While if G is infinite, then the notation we use is order of G equals infinity. Now, let's talk about the order of an element in a group. Given a group element A, we say A has finite order if there exists a positive integer n such that A to the power of n is equal to the identity. And in this case, the order of A is the smallest positive integer with that property. And we say A has infinite order otherwise. That is, A has infinite order if there is no positive integer n such that A to the power of n is equal to the identity. And in this case, we use the notation order of A equals infinity. Now, some properties that we have proven regarding the order of a group and the order of elements in a group are as follows. Every element of a finite group has finite order, and given a group element A with order n, then the group generated by A consists of precisely the elements A to the power of 0, A to the power of 1, A to the power 2, A to the power of n minus 1. Moreover, if we're given integers I and j which lie between 0 and n minus 1, then if I and j are distinct, then A to the power of I and A to the power of j are distinct. So that essentially tells us that all of these guys are distinct. And we're also going to be using the concept of a finite set in proving this theorem. And our definition is as follows. For each integer n greater than or equal to 0, let In be the set of integers between 1 and n. For example, this is what these sets would be. Well then, given a set A, we say A is finite if there exists an integer n greater than or equal to 0, such that there exists a bijection from In to A. And this is the notation we're using to say there exists a bijection from this set to this set. And in fact, n is unique, meaning n is the only integer greater than or equal to 0 that will satisfy this statement. So, if we know of two integers greater than or equal to 0, n1 and n2, such that there exists a bijection from in1 to a, and there exists a bijection from in2 to a, then n1 and n2 are equal. So n is unique, and we call this unique number n the number of elements in A, and we write it like this. Okay, so now let's get into proving this theorem. Now the whole goal is to prove that the order of A is equal to the order of the group generated by A. And to prove that, we're going to split this up into two cases. Either A has finite order or A has infinite order. Let's first consider the case A has finite order. And we'll say that the order of A is equal to the positive integer n. From here, we want to show that the group generated by A also has finite order, and we want to show that its order is equal to n. To do that, we are going to apply the definition of a finite set. So we want to find a bijection from In to the group generated by A. And we consider the following function. We consider the function f from In to the group generated by A by mapping each integer in In to the element A to the power of I minus 1. The claim is that this function is a bijection from In to the group generated by A. And to prove that it's a bijection, we're going to show that it's injective and surjective. So let's first verify that f is injective. To prove that f is injective, let's give ourselves two arbitrary integers I and j in In. And to prove injectivity, we want to show if f of I is equal to f of j, then I is equal to j. So let's suppose f of I is equal to f of j. Well then, by definition of our function, we know that f of I is equal to a to the power of I minus 1, f of j is equal to a to the power of j minus 1. Now, since I and j are elements of In, this means that I and j are integers which both lie between 1 and n. But then, if we subtract 1 through these inequalities, we get that I minus 1 and j minus 1 lie between 0 and n minus 1. But now, let's apply star star. Applying star star, we're going to take I to be I minus 1. We're going to take j to be j minus 1. Well, we know that I minus 1 and j minus 1 both lie between 0 and n minus 1. So this condition is satisfied. So, with our choice of I as I minus 1 and j as j minus 1, this statement is saying if I minus 1 is not equal to j minus 1, then a to the power of I minus 1 is not equal to a to the power of j minus 1. But we're going to apply the contrapositive of this statement. The contrapositive tells us if a to the power of I minus 1 is equal to a to the power of j minus 1, then I minus 1 is equal to j minus 1. But we know that a to the power of I minus 1 is equal to a to the power of j minus 1. That's what we have here. So we can conclude that I minus 1 is equal to j minus 1. So adding 1 on both sides, we get I is equal to j. So we've shown if I and j are any two elements of In, well then if f of I is equal to f of j, then I is equal to j. So this shows f is injective. Now let's show that f is surjective. To prove surjectivity, we want to prove for every element q in the group generated by A, there exists an element I in In such that f of I is equal to q. So let's give ourselves an arbitrary element q in the group generated by A. Now since q is an element of the group generated by A, well, by star star, we know that the group generated by A is precisely this collection of elements. So q must be equal to a to the power of k for some integer k that is between 0 and n minus 1. Well then, if we add 1 through this inequality, we get that k plus 1 lies between 1 and n. And that tells us k plus 1 is an element of In. So since k plus 1 is an element of In, that tells us k plus 1 lies in the domain of our function f. So computing f of k plus 1, we have f of k plus 1 is equal to a to the power of k plus 1 minus 1. And k plus 1 minus 1 is equal to k, so this is just a to the power of k, and we know that a to the power of k is equal to q. So putting this together, we have shown, given any element q in the group generated by A, there exists an element in In, namely k plus 1, such that f of k plus 1 is equal to q. And this shows that f is surjective. So we have f, a function from In to the group generated by A, that is both injective and surjective. That tells us that f is a bijection from In to the group generated by A. Because we now know that there exists a bijection from In to the group generated by A, this tells us, by definition of a finite set, that the group generated by A has n elements in it. And n is also equal to the order of A, so this shows that the order of A is equal to the order of the group generated by A. So this completes the case where A has finite order. Now let's consider the case A has infinite order. Now the notation we use to say A has infinite order is we say order of A equals infinity. right? This is the notation we use. So in this case, we want to show that the group generated by A has infinite order, because that will tell us the order of the group generated by A equals infinity, right? That's the notation we use, and hence the two orders are equal. So how do we prove that the group generated by A has infinite order? Well, one way to do it is assume for a contradiction the group generated by A has finite order. Now, we know that every element of a finite group has finite order. So in particular, since A is an element of the finite group, the group generated by A, that tells us A must have finite order. But really, this is saying A has finite order in this group. But since the group generated by A is a subgroup of G, that means A has finite order in G as well, right? The order that A has in G is equivalent to the order that A has in any of its subgroups. So A has finite order in G, but that contradicts the fact that A has infinite order in G. Our assumption that the group generated by A has finite order led us to a contradiction, so we must instead have the group generated by A has infinite order. And the notation we use is order of A equals infinity, which is equal to the order of the group generated by A. So their orders are equal. And so we see in either case, whether A has finite order or infinite order, the order of A and the order of the group generated by A are equal. So this completes the proof. Now, an alternative way to show that the group generated by A has infinite order is to establish a bijection between the integers and the group generated by A, right? And all you have to do is send each integer I to the element A to the power of I. This will give us a bijection between the integers and the group generated by A, and that implies that the group generated by A is infinite. Now, if you don't like the notation order equals infinity, then another way of looking at this is it's saying A has finite order if and only if the group generated by A has finite order. And in this case, the order of A and the order of the group generated by A are equal. And A has infinite order if and only if the group generated by A has infinite order. And so yeah, that's pretty much it for this video.